Okay, sir. Mm, Okay, okay, sir. Thank you for giving me the opportunity to give the expert session on the MOSFET and BiCMOS. Okay. A very good afternoon to all the students, all the aspirants who want to continue their career in core related, either it may be embedded or VLSI or it may be communication. Okay. So who are passionate about VLSI, they need to know more about this MOSFET and BiCMOS. I'm sharing the screen. One second. Yeah, yeah, 1 second. Mm, Yeah, screen. I'm sharing this. Okay. Today we discuss about these. So today we'll discuss about the outline in this. Okay. Uh, so please mute yourself during my session. Okay. Today we discuss about the how the MOSFET is acting as a switch and MOSFET as a inverter. Yeah, some disturbance is coming from the. Yeah. Please mute yourself. Hello. Yeah, we'll discuss about MOSFET as amplifier, how the MOSFET is. Yeah, yeah, yeah. Please just engage, sir. Okay, thank you. So my voice is clear, no? Shall I move forward? Hello. Shall I move forward, sir? Am I audible? Give response. 1 second. Yes. Yeah, yeah. Now I'm audible. Yeah. I'm audible, sir. Kamalkal, sir. Okay. Okay. Sure, sir. Okay. Thank you. Yeah, yeah, yes, sir. Sir messaged me. Yeah, yeah. Okay. So today we'll discuss about how the MOSFET is acting as a switch and MOSFET as inverter and MOSFET as the amplifier and small signal voltage gain and other MOSFET applications and recapitulation. Okay. So normally like MOSFET operation, you already seen like MOSFET, you have like enhancement MOSFET and depletion MOSFET. Just I'm going through that operation so that you can understand the how the MOSFET is acting as a switch. So MOSFET is two types like enhancement MOSFET and depletion MOSFET. Enhancement MOSFET is nothing but there is no channel, and depletion MOSFET is nothing but there is already channel is there. And again, those are divided into two types like P channel MOSFET and N channel MOSFET. In N channel MOSFET, means the current is due to the electrons in the channel. N channel means electrons. Okay, and in P channel, the current is due to holes. Okay, and that is enhancement MOSFET. So the channel is not there. You need to apply the positive voltage for enhancement N channel MOSFET so that we can induce the channel. We can internally develop the channel. Those are operated. So similarly, here in P channel enhancement MOSFET, we are applying negative gate voltage so that channel is developed due to holes. Okay, and so depletion MOSFET is already channel is there. Okay, already channel is there. So we are like we are that will be operated in both modes. Either it is enhancement mode or depletion mode, depending on the gate voltage we are applying. Suppose example, if you take depletion N channel MOSFET, so if you apply positive gate voltage, that is acting as the enhancement MOSFET, and negative gate voltage, a depletion MOSFET. So those are these are different types of operations. You already seen, I think so. So it is operated in cutoff region, and linear region, non-linear region, and saturation region, depending on the VDS we are applying. So in the linear region, channel will be uniform and it is acting as a resistor, and in non-linear region, channel will move from. So channel will be non-uniform, and the drain current will increase, but the rate at which the drain current will decrease. And after that, channel will be pinched off, and it will going from where to where drain to source. Okay, that is nothing but punch through. Due to that, the drain current becomes constant. And what happens when the drain current becomes constant? There is no way depending on VDS. There it is depending on VGS. Okay, so that all are operations. I think sir already explained. Now today our agenda is how the MOSFET is acting as a switch. Okay, So normally, if you say like it's switch means what in your household or any other application. So when you are switching on, that is nothing but resistance is low, and that is nothing but current is high. Okay, it resistance will be low and current is high. Current, more current will flow into this, into that. And when switch is off, so resistance will be more, resistance will be high, and there is no direction of the current. Okay, exactly same concept we are applying to this MOSFET. Okay, so MOSFET is nothing but you know that metal oxide semiconductor field effect transistor. So the current, this is a voltage control device, and the current is due to only majority carriers. Okay, another name for MOSFET is IGFET. Okay, insulated gate field effect transistor. Okay, so here if you see, this helps, so that means so which one is controlling this this MOSFET as a switch means yeah, gate to source voltage. This is nothing but VGS is controlling the gate to source voltage. So that means if you take the enhancement MOSFET, so when VGS is less than VT, there is no channel formation. Okay, there is no channel formation. ID equal to 0 means it is acting as off switch. Okay, when VGS is greater than or equal to VT, okay, greater than or equal to VT, then there is a some ID current. Okay, it is a like a channel is forming, and that is nothing but strong inversion layer. Okay, so when it is channel is forming, it is going to linear region, non-linear, and saturation region. This we call as on switch. Okay, these are the conditions. Okay, so for what value of gate voltage will turn on means threshold voltage. So this is nothing but what VGS is greater than VT. Okay. For what value this is resistance between source and this is off switch means when VGS is less than VT. Okay. So VGS decides whether the my MOSFET is acting as a switch or not, and this limits the speed of the device. Okay. This limits the speed of the device. Normally, like so that means so here gate is acting as a controlling switch. Okay, normally gate is acting my gate is acting as a controlling switch. Okay, controlling switch. So that means suppose if it is on switch, R on equal to what? R on is less. Okay, when it is off switch R on, what is my R on will be more. Okay, so normally the speed of any circuit is denoted in terms of resistance and capacitance, RC. Okay, so RC is nearly equal to what? Tau. Okay, so tau means what? When, so that means when RC is low, tau is slow. Okay, so tau is low means what? It is acting as on switch. Okay, and when RC is high, when R is high, and tau is also high. Okay, tau is also high, and it is acting as what? Off switch. It is acting as off switch. Okay, so normally we know that frequency is reciprocal of tau. Okay, so that means when tau is low, frequency is high. Okay, so you need to see about the speed of this circuit. Yeah, yes. One second. Okay, one second, one second, one second, one second. Yeah. Okay, okay. Now it's audible, sir. Okay, it's yeah, automatically it is going into mute state. Okay, yeah. So this is about so just please inform sir so that I will check for my mic. Okay, yeah, yeah, yeah. Thank you. Okay. So this is about the MOSFET as a switch. Okay. So normally like MOSFET, you are so this is the diagram how the MOSFET is acting as a switch. Suppose like you are applying gate to source voltage as 0. Okay. When you are applying gate to source voltage as 0, so what happens? It is acting as a like it is off actually in my NMOS. Okay. So this is my what is this enhancement uh, NMOSFET. Okay, N channel MOSFET. Okay, so how you will identify this is dash line is there, no? Channel already channel, no channel is there. No channel is there means what? So that means we need to induce the channel by applying gate voltage, and the channel is due to electron. That's why the arrow is towards the this direction. So when you are applying gate to source voltage as 0, it will be off switch. Okay, it will be like it is acting as open circuit. Okay, so when it is open circuit, whatever the VSS is there, it is coming to the V naught. Okay, VSS or we can call as a VSS or VDD also. So that means it will be like 5 volts. Okay. So that means when VI equal to 0, so device will be off. Okay, this device will be off, and you are getting V out equal to what? Vs. V out equal to Vs. Okay. And next, I'll change the color. Suppose when this one is 1. Okay, when input is 1, so this will be on, this will be on. So when this will be on, it is acting as what? It is acting as closed switch. Okay, so it is acting as closed switch. Suppose if you consider, yeah, some capacitor is there, means that capacitor is charging and discharging. So when it is a closed switch, whatever VDD is there, it is going into ground. So that means you are getting V out equal to what? V out equal to 0 you are getting. Okay. So that means when V input equal to 0, you are getting VSS. That means plus 5 volts. Okay, plus 5 volts. And V input equal to 1, you are getting 0. That is 0 you are getting. Okay. So like this, it is acting as on switch and off switch. Okay. It is acting as on switch and off switch. Okay. This is the operation of normal my MOSFET. Okay. MOSFET. So coming to the CMOS, CMOS is nothing but complementary inverter construction. Okay, complementary MOSFET. So complementary MOSFET means what? You have PMOS as pull up, PMOS as pull up, and NMOS as pull down. Okay, so this is nothing but PMOS as pull up. PMOS is nothing but with bubble will indicate, and NMOS as pull down. Okay, NMOS as pull down. So so this gate is commonly connected to this input. Okay, and both drains are connected together. See here, this is source, drain. Both drains are drain of PMOS and drain of this NMOS. Both are connected together, and this is source. This you can consider as ground or VSS. Ground or VSS. Okay, PMOS is connected to VDD. Okay, so what happens when you are giving 0? When you are giving 0, this will be what? This will be on, and this will be off. Okay, this will be off. Okay, so what happens? Suppose the circuit will look like this. Okay, so this will be on means short circuit, and this will be off means open circuit, and this is anyway ground. You are getting ground, and this is VDD. Okay, here you applied the input voltage 0. So that means whatever the VDD is there, you are getting is the output. That means this is plus 5 volts. Okay. So that means if you are giving as a logic 0, you are getting logic 1. Okay. So this is first operation. And next second operation, if you see, I'm changing the color. Suppose if you give 1 for the inverter, you need to get 0. Okay. So that means when you are giving 1, this will be off and this will be on. Okay, so when this will be off, like this is open circuit. Okay, this is open circuit, and PMOS is open circuit and NMOS is short circuit. Okay, so here you are giving 1, you are getting what? There is no supply between VDD and output, so this ground is connected to output. That means you are getting what? 0. Okay, so when you are giving 1, you are getting 0. Okay, so like this we can use CMOS as a basic inverter. Okay, so when V input is 0, so Q1 is on and Q2 is off, you are getting V out equal to VDD. That is logic 1. When V in equal to 1, your Q1 is off and Q2 is on, you are getting this is ground. Okay, so this I took from the Microelectronics by Sadre and Smith, 5th edition. Okay, and so this is about the CMOS inverter. Normally you can connect the capacitor also. So here you can connect the capacitor. So that means when it is 0, it is capacitor is charged through the VDD. Okay. When it is 1, capacitor is discharged through the VDD. Okay. There is no open circuit like that. Okay. So next, CMOS we can use as a MOS inverter. Static behavior. What is the static behavior? Like you have noise margin. Okay, noise margin. What is noise margin? Noise margin is nothing but maximum noise voltage which can sustain by the inverter is nothing but noise margin. Okay, suppose if you have noise margin is zero point 0.1 volts. Okay, if you have noise margin as zero point 0.1 volts, inverter able to reject it and move forward. Okay, inverter can reject this noise margin. Okay, and it will move forward. So that means ideally if you consider this noise margin should be what? should be noise margin meaning is large voltages can remove the large noise voltages. Noise is nothing but unwanted voltage. Okay, so large noise voltages. Noise voltages are removed by the CMOS inverter. Okay, removed by this CMOS inverter. This is one of the advantage of the CMOS inverter. Okay, so that's why it is having high noise margin. Okay, ideally equal to what? So noise margin ideally equal to supply voltage. What is the supply voltage we did? Okay, and ratio is ratio less logic level, and low output impedance and high input impedance. So why it is high input impedance? So if you consider MOSFET, okay, it is consist of PMOS and NMOS. So this is N plus and this is N plus, and here you have SiO2 layer. Okay, and here you have polysilicon. Okay, so for the gate, so that means normally gate current equal to 0. Gate current equal to 0 means what? You are having high input impedance, improved input impedance. Okay, and it will improve the fan out. Okay, low output impedance, and no static power consumption. No static power consumption means when CMOS is in off state. Okay, CMOS is in off state. What happens? So NMOS will be off, and PMOS is also in off. Okay, so that is nothing but no static power consumption. During the off state also, it will not consume any power. That is nothing but static power consumption. Some circuit, when they are off only, it will take some. It will be say some switching power. Okay, so that is nothing but static power consumption. And so this is about the MOSFET switch. Okay, first I told you about MOSFET as a switch, how it is acting as a switch. So here there is a control, gate control, that is acting as a switch. Okay, we already seen, and how it is acting as a switch we seen, and CMOS inverter, and what are the behaviors, what are CMOS inverter static behaviors. Next, coming to the MOSFET as an amplifier. Okay, so how it is acting as an amplifier means, so here if you see MOSFET, normally there is like this is nothing but basically characteristics we can call as a drain characteristics. Drain characteristics. Okay, I told you know it will be operated in four modes. One is cutoff region. One is cutoff region. Next one is linear region, and next one is non-linear region, and the next one is saturation region. Okay, so if you consider this curve, normally this is cutoff region. This is nothing but cutoff region. Okay, and this is up to here. The curve will be straight. It is acting as a resistor. This is linear region, and this is non-linear region. This is non-linear region, and after that, this is nothing but saturation region. Current will becomes constant. Okay, so if you draw the DC load line, this is nothing but what? A DC load line. Okay, this is we can call as load line. Okay, load line. So there is a Q point. There is a Q point. It is center between this drain and VDS. Okay, if you draw the straight line, it will intersect the middle part. That is nothing but Q point. Okay, so here this Q point, this VD sat is nothing but what? VD sat is nothing but when this is the drain to source voltage, the channel is pinched off. Okay, so when it is pinched off, that means VDS sat, that is equal to what? Overdrive voltage, that is VGS minus VTN. VGS minus VTN. Okay, and when it will be going into saturation region means it should overcome that pinch off point, and that should be greater than VGS minus VTN. Okay, then only it will go into the saturation region. Okay, so if you draw the time this waveform, so here this with respect to Q point, so here in the output you are getting like this, and here if you draw here, so this is the 180 degrees phase shift. This is nothing but you are getting 180 degrees phase shift. Phase shift. Okay, 180 degrees phase shift. Okay, so here so this is so basically I'm talking about common this is a common source amplifier. Common source amplifier means what? The source is there, no? Source is connected to ground, and it is common for both input and output, and this is a drain. and this is gate. You have drain resistance, and as this is enhancement MOSFET, electrons will flow from source to drain. There is a conventional current. The current will flow from drain to source. Okay, this is the electron movement. So this is the drain current. Okay, this is VDD, and input voltage is VGS you are applying. Okay, so this is the basic diagram of amplifier. Okay, so coming to this MOSFET as an amplifier, how it is acting as an amplifier means here how the amplification is taking. So first of all, I want to say why it is phase shift. Okay, so if you apply KVL, okay, so this is what this is positive negative, and this is positive negative. Okay, so rise in voltage equal to drop in voltage, no? So that means you are getting VDD minus IDRD minus VDS equal to what? 0. Okay. VDS is equal to V naught only. Here VDS equal to what? V naught only. So from here what you are getting V naught? V naught equal to VDD minus IDRD. VDD minus IDRD. So that means as ID increases, so as ID increases, V naught decreases. Okay. So V input increases, ID increases. As ID increases, V naught decreases. Why? Because this is negative. This is nothing but negative. Okay. So this will decrease. Okay. So if you take the common source amplifier, so this is a normal common source amplifier, as I told you. Okay. Uh, so so if you see the input and output characteristics, so that means here what happens means here till here this is constant. After that this will decrease like this. Input, as you increase the input voltage, the output voltage decreases. So as I told you, know V naught equal to what? ID. V naught equal to previous slide I told you. V naught equal to VDD minus IDRD. So VDD minus ID RD. From this only, if you increase the input voltage, this input voltage, okay, ID increases. ID increases. As ID increases, what happens to V naught? V naught decreases. Here V naught decreases. So goes on decrease like this. Okay. So here, if you see, this is so this is a equivalent circuit in triode region. Triode region means you know that the our MOSFET is operating in both what we call linear region and non-linear region. Linear region and non-linear region. Okay. So so that means this is acting as a resistor. Normally we can call this as a R-on. Okay, this is nothing but we call as R-on. Okay. So this is a small signal model of our MOSFET in saturation region. So this is V input, and input impedance is more, no? So that means at input side this is open only, and this is nothing but what we call yeah, this is you have independent source and dependent source. No, this is dependent current source. Dependent current source. Okay, so dependent current source means you have like voltage controlled voltage source, voltage, so voltage controlled voltage source, voltage controlled current source, current controlled voltage source, current controlled current source, like that. Okay, so this is my current source, this is my current source, depending on which voltage? Input voltage. So this we can consider as voltage controlled current source. This is nothing but voltage controlled current source. So what is this value? Gm into V1. That is nothing but Gm is nothing but transconductance. Gm is nothing but transconductance, and RD is nothing but drain resistance. RD is nothing but drain resistance. Okay. So here if you see, so if you see that so current when M1 is in saturation, normally what you got? V out equal to VDD minus IDRD. Okay, IDRD. So what is the current equation in saturation? So ID equal to 1 by 2 mu n COX W by L V in is nothing but VGS only, VTH whole square. Okay, so this is my current equation in saturation, ID. Okay, so anyway, from here you can say that V out equal to V in minus VTN. Okay, VTH. V out equal to what? Here V out equal to I can say that V in minus VTH. Okay, V out equal to, you can consider as V in minus VTH. Okay, so this I am substituting. Okay, this I am substituting, and next what I am doing, as V in is more value than V in 1. Okay, V in 1, then M1 is acting in a triode region. Triode region means what? Either it may be, here I am neglecting the channel length modulation. Okay, channel length modulation lambda I am neglecting, and I am approximating. Okay, so linear region, what is the current drain current equation? ID equal to 1 by 2 mu n COX W by L, 2 into V in minus VTH into V out minus V out is nothing but VDS. Okay, V out square, V out square. Okay, so this is my ID equation. This total, where mu n is nothing but mobility of electron, and COS is nothing but a insulator capacitor. Okay, capacitor SiO2 layer is there, no, that is nothing but capacitance of oxide layer. Okay, so this is my ID. This is my ID. Okay, so that means M1 in deep triode region, as a V out is less than V2 into V in minus V in minus VTH. If you approximate, you will get V out equal to R on by R on plus RT. Okay, you will get this equation. Okay, and that is equal to VDD by 1 plus mu n into COX W by L RD into VTN minus VTH. Okay, so that means from this, I can say that for the small signal amplifier, I think this analysis you already did. What is gain? Gain equal to what? AV equal to V out. So V out by V in, V naught by V in. Okay, V naught by VI. This is voltage gain. And current gain. Am I audible, sir? Yeah. Okay. 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 Yeah. Some disturbance is coming. Some disturbance is coming. Yeah. Yeah. Please see on that. Okay. So here current gain equal to VI by V no I naught by II. I naught by II. I naught by II. Okay. So normally if you means rearrange, so mostly AV you are getting minus GM into RT. Okay, minus GM into RT. So GM into RT means what? So that means so so here current gain, one way to get the large voltage gain is so you need to you need to increase the transconductance. You need to increase the transconductance, or RD the point not go idea to increase RD. Okay, so RD we can't increase. Why? Because this is fixed value only. Okay, and so we can increase the transconductance also. Okay, we can increase transconductance. Okay, and so this is one way we can increase the current gain. And next, how to maximize the voltage gain in the common source stages? This is my formula. Okay, so from this I can say that voltage gain is directly proportional to the oxide capacitance. Voltage gain is directly depending on the aspect ratio W by L. Okay, and it is depending on what VRD. Okay, drain voltage. Okay, so in order to increase this voltage gain, we need to prefer this aspect ratio as large. Okay, mostly we will prefer. Okay, we need to design a transistor such a way that we need to design in a WL should be more. Okay, or otherwise previously you got, no. So this means you got, it is depending on transconductance. So that means when the transistor is operated here or here, you are not getting maximum gain. So my transistor should operate at maximum transconductance. Okay, maximum GM. Then I will get good gain. Okay, so this is how to maximize the voltage. We can increase the oxide capacitance is constant only. No, oxide capacitance we can't change. We can change the W by L ratio. That depends on the possibilities. Okay, that it depends on the possibilities, what the transistor you are using, and those things. Okay, and cost also depends on size, cost we need to consider. Okay, we can make this also large. Okay, So like this we can increase. Okay. Uh, and one more thing, like if you increase the two transistors in cascade, you can get the maximum gain as what you can try this. Yeah, so suppose first stage is this one. You can multiplication of this second stage, AVS2, okay, AVCH2, okay. Suppose first stage have gain of 10, second stage has gain of 10, it will be multiplied and you are getting 100 like that, okay. Like that also by cascading also you can increase the gain, okay. So this is about the basic MOSFET is acting as a transistor. Okay. So this is the MOSFET as a transistor. First we seen about the characteristics and Q point, DC point, and based on that we discussed about the MOSFET as an amplifier at different conditions. Okay. So MOSFET is depends on which one, that is GM. Okay. It is depends on GM and depends on the aspect ratio and like that we discussed. Okay. So this is about MOSFET is acting as a amplifier. Okay. And next, so where you are using the MOSFET, we are using in digital logic circuits or unlock circuits. We are using this MOSFET. Okay. And so this is about the MOSFET. Next, next I will go with the BiCMOS inverter. Okay, BiCMOS inverter. So what is this BiCMOS inverter means? BiCMOS inverter. So normally BiCMOS technology. So if you consider BiCMOS technology, one second, I'm changing the color. Yeah, yeah. So BiCMOS technology. BiCMOS technology means here bipolar plus CMOS technology we are using. Bipolar plus CMOS technology we are using. Okay. So bipolar and CMOS technology we are using. Okay. So that means uh, so here bipolar is nothing but what BJT. Bipolar is nothing but BJT, and CMOS is nothing but it consists of what NMOS as pull down network and PMOS as pull up network. Okay, NMOS as pull down network and PMOS as pull up network. Okay, so that's PMOS technology. Okay, so why we are using means here. Suppose if you consider CMOS. Okay, CMOS. What are the advantages? Advantages are low power consumption, low power consumption. Okay, this is the advantage of CMOS. Okay, what is disadvantage? Disadvantage is slower than BJT, lower than BJT. Okay, lower than the BJT. And next, coming to the BJT, coming to the BJT. BJT, what are the advantages? Advantages is this is the speed of operation, then then CMOS. Okay, and what is disadvantage? What is disadvantage? High power consumption. High power consumption. Okay, so high power consumption. So here what I am doing means I'm adding means by using BiCMOS technology I'm adding these two properties. What is that property? By using CMOS I'm adding low power consumption. By using BJT I'm increasing the speed of the operation compared to CMOS. Okay, I'm increasing the speed. So I'm going into the BiCMOS technology. Okay, so that means you have CMOS. Okay, this is nothing but CMOS along with the BJT. This is nothing but BJT. Okay, so how you evaluate? This is nothing but inverter only. This is nothing but what? Inverter only. Okay, so if you are giving 0, you need to get 1. If you are giving 1, you need to get 0. Okay, so how you can analyze this? Suppose here I'm writing input, input, transistor, transistor output. Okay, so here if you see, yeah, so input transistor output. Okay, so when input is 0, when input is 0, so tell me T3 means what? PMOS will be on, no? So this is PMOS and this is NMOS and this is NPN transistor and this is also NPN transistor. Okay, so this. This one is there, no? This symbol says that when it is inside means PNP transistor. Okay, that knob notch is there, no? Notch you can identify. So T3 is on, and T4 is on. Okay, T4 is off. NMOS is off. T4 is off. Okay, so here, this is off means what? So this is off means. One second. One second. Sorry. Sorry. One second. I told reverse. Yeah. So when the input is 0, PMOS is on and NMOS will be off, no? So when input is 0, PMOS will be on. Okay. So that means T3 is on and T4 is off. Okay. So when T3 is on, so you are getting some signal or one signal to this one, to the base of this transistor. T1 is also on. T1 is also on. So there is no signal for T4. That means T2. T2 is off. Okay. So that means this is short circuit, and from here this T1 is also, it is acting as a short circuit. So this VDD, so how the path will be there? So how the path will be there? Like this, that capacitor will charge. Capacitor will charge. So that means here you are getting CL is charge. Okay, CL will charge. CL will charge. So that means if you are giving 0, you are getting VDD. VDD at output. That means plus 5 volts. So this is 1. This is 1 we are getting. Okay. One more case we'll see. Input, transistor, transistor, output. Okay. When you are taking this as 1, okay. Now T3 is what? PMOS will be off, and T4. T4 means what? T4 will be on, and T1 will be off. Okay. And T2 will be on. As the T3 is off, there is no signal to this one. That's why T1 is also off. And T2 is on. That means you are getting the signal from here and it is short, and it is coming to here, and this is you are getting some voltage and it is also on. Okay. So that means what happens? There is a no connection between these rail. Okay. There is no connection. No connection from this rail. Okay. So the connection is from, it is going to this one. Okay, capacitor is not coming. So this is open circuit only. This is open circuit only. Here what happens? Capacitor will discharge. When the capacitor is discharging, it is going into 0. So when you are giving 1, you are getting 0. You are getting 0. Okay. Uh, so if you see what is the drawback in this circuit means, there is one drawback is there. There is nothing but static current flow. So static current flow means what? Like when what happens when problem is when T4 is on. When T4 is on, T2 is also on. Okay. When T4 is on, T2 is also on. So what happens? There is a current, that static current that flows from where to where. So from here T4 to T2. T4 to T2. Okay, there is a static current. Okay, so what happens due to this? There exists a static current flow. There is maybe damage of transistor also, damage of the transistor also, or low impedance path is there from VDD to supply voltage. Okay, so that is one disadvantage of the circuit. To overcome that, we are going with this circuit. This is nothing but modified, modified by CMOS technology, by CMOS inverter. So here, what is the change? Here, this path is there, no? This path I connected here. I connected here. Okay, see here, so that we can avoid the static current flow. Okay, so we can avoid the functionality is same only. Okay, functionality, it is acting as inverter only, but in order to avoid the static current flow, we are rearranging my circuit. Okay, so this is the basic inverter by CMOS inverter circuit. Hope you understood. And next you see, so logic gates means suppose normally, like when you start any technology, we'll start with basic inverter. Okay, where they will explain with basic inverter. It may be NMOS technology, CMOS technology, or BiCMOS technology. Okay, next they will come with the two input, that means a NAND gate, two input NOR gate. These are nothing but universal gates, no? So we can design the two input NAND gate by using NMOS, CMOS, and BiCMOS. Okay, so we can design by two input NOR gate by using NMOS technology, CMOS technology, or BiCMOS technology. Okay, so how we can design, I will tell you. So that means NMOS means what? All are NMOS only. All are NMOS only. CMOS means it consists of PMOS as pull up and NMOS as pull down. Okay. BiCMOS means you have bipolar. Bipolar means we already discussed BJT and CMOS. Okay. BJT means you will get a NPN transistor, PMOS transistor, and MOS transistor. Okay. So if you see this one, this is a basic inverter. So this is NMOS inverter. NMOS inverter means this is nothing but a depletion MOSFET. Depletion MOSFET. Depletion MOSFET means what I told you. Already channel exists. Okay. So that means already channel exists means let us take drain. Both drains are connected together. No, this is drain and this is drain, and this is source and this is source. Okay. So this gate is connected to drain. This is always on. This is always on. Okay. So it is acting as a load. Okay. It is acting as a load. And so what happens? Suppose if you are giving zero, we are giving 0. So below there is a NMOS transistor. NMOS transistor. This is enhancement. This is enhancement NMOS transistor. So when it is 0, it will be in off state. It is in off state. So this will be open circuit. This will be open circuit. So whatever the VDD is there, you are getting at the output. You are getting 1. Okay. We are giving 0, you are getting 1. Okay. And next, if you are giving, I'll change the color. Yeah. If you are giving 1, okay, 1. So this will be on. This will be on. This is always on. There is a path from VDD to ground. There is a path from VDD to ground. So what happens? So that means output is connected to ground. You are getting 0. So when you are giving 1, you are getting 0. Okay. And this is nothing but CMOS. I already told. So we already discussed in the previous session. CMOS complementary inverter. Okay. So that means when it this is so this is basically current direction, and this is 4 terminal, this is connected to source like that. Okay, and this is one more representation with bubble. With bubble, if you represent, this is PMOS and this is nothing but NMOS. Okay, NMOS. Okay, so that means when it is 1, PMOS will be what? When it is 0, PMOS will be on and NMOS will be off. Okay, so directly it is on means VDD you are getting 1. Okay, when it is 1, PMOS will be off and NMOS will be on. Okay, NMOS will be on. So that means there is no supply from VDD to output, you are getting 0. So inverter properties are happening. Okay, 0, 1, 1, 0. This is by CMOS we already discussed. Okay, no need to say no. So it is acting as inverter 0, 1, 1, 0. Previously we discussed the inverter of by CMOS. Okay, and this is nothing but NAND gate. Okay, normally we'll represent NAND gate. NAND gate means suppose you need to remember this. Suppose in CMOS or any inverter realization, uh, suppose if it is AND operation, if it is AND operation, PMOS will be what? PMOS will be NAND, no, parallel. PMOS will be parallel, and NMOS will be series. NMOS will be series. Okay. If it is R operation, PMOS will be series and NMOS will be parallel. NMOS will be parallel. Okay. So see here. So that means here you are using depletion type MOSFET. Depletion type MOSFET. This is always on. And here in pull down you have NMOS. NMOS is inside to be in what series. So this is an AND, no? AND means what? So Y equal to A and B whole bar. A and B whole bar. Okay, and operation with complement. Okay, and if it is CMOS, PMOS will be in which one? Parallel. This is parallel. Okay, parallel, and NMOS will be series. NMOS will be series. Okay. Similarly, this is BiCMOS. BiCMOS means what? PMOS will be parallel. and NMOS will be series. And similarly, that is connected to these transistors by CMOS. Okay. Similarly, NOR gate also. NOR gate means what? This is depletion MOSFET, always on, and when it is OR operation, so this is nothing but ARB whole bar. ARB whole bar. ARB whole bar means what? These are said to be parallel. These are said to be what? Parallel. Okay. And here PMOS is in series and NMOS is said to be in parallel. In parallel. This is NOR operation. And similarly, here also PMOS will be series and NMOS will be parallel, and it is given to two more NPN transistors. That is nothing but BiCMOS technology. BiCMOS technology. Okay. So this is about two input NMOS, CMOS, and BiCMOS NOR gates. Okay. So this is about the this one. And next, we'll see the PLDs, programmable logic devices. So programmable logic devices are basically three types are there. Okay. Normally, what is programming? Programming is nothing but the process of entering the information to the devices is known as what? Programming. Okay. So programming is refers to what? Hardware programming. Okay. So you have AND array and OR array. Okay. So there are three kinds of programming PLDs are there. One is programmable read-only memory, programmable array logic, programmable logic array. Okay, that we'll see. Okay, so programmable read-only memory means what? So this is nothing but ROM. Okay, PROM means what? ROM. So this is non-volatile. Non-volatile. Non-volatile means what? When the power is cut down, whatever the data or whatever the softwares are there, those are available in your system. Okay. So that means basically whatever the OS related and your files are there that are stored you are in the ROM. No. So nowadays SSDs are coming in the laptop. Okay. Previously there are hard disks are there, magnetic hard disk are there, HDDs are there. Now SSDs are coming. So SSDs are nothing but we can call as solid state devices. Okay, solid state devices. So noise will be less, and these are nothing but means non-volatile only. So whatever the data is there, that we will store. RAM is nothing but read write memory or random access memory. So this is volatile. This is volatile. Normally, like whenever if you want to do some operations temporarily, so temporary processing is done in the RAM. Okay. So when the power is cut down, all data will be erased in the RAM. Okay, like that. So here if you see, this is flexible to program the binary information electrical only by fusing. Okay, you have fixed AND array and programmable OR array. Okay, it generate the all the terms, fixed AND array and programmable OR array. Okay, so how you can design the fixed AND array? By using 3 to 8 decoder. By using 3 to 8 decoder, you will get all the minterms. Okay, suppose if I want to explain with this example, see here two functions are given. Okay, you need to implement with one is programmable read only memory. So how to implement? So here first stage is inputs are x, y, z, and outputs you need to initialize with what? This minterms. What? 567, 567. Okay, and this is nothing but a connected with our OR gate. So OR gate is programmable, and this is sorry, OR gate is programmable, AND gate is fixed, AND array is fixed, OR array is programmable. Okay. Similarly, these minterms are there. So just minterms you program this and connect to the OR gate. Connect to the OR gate. Okay. So this requires 3 to 8 decoder and programmable OR array. Okay. Similarly, PAL is there. PAL means what? Programmable AND array and fixed OR array is there. Okay. AND array will be programmed like fusing programmable OR array, AND array, and fixed OR array means nothing but what? Like this is there, fixed OR array. Okay. And so I can tell you with one example. So you take two examples: xy plus xz dash, y dash plus yz dash. Okay. So this is programmable, no? Programmable AND array. Okay. So you take x and this is nothing but x dash, and this is y dash, this is z dash. Okay. So x x y, this is xy. Okay, this is xy, and next x z dash, x z dash. Okay, and next x y dash, x y dash, okay, x y dash, y z dash, y z dash, okay. This is connected with the AND gate, AND array, and after that this is nothing but fixed OR array. So what is my first function? This is x y x z dash. It is connected with OR gate, okay. It is connected with OR gate. Similarly, x y dash, x y z dash, y z dash, okay. So this is connected with OR gate. Like this I can implement it, okay. PLA is nothing but what? Programmable logic array. Both are programmable. So programmable AND array and programmable OR array. Okay, both are programmable. Okay, that is nothing but PLA. Okay, so PLA if you see, so same function I am taking. So same function, not same function. This is different function only. So this I took same function only. So this is not xy, and this is x z dash. Okay, this is x dash, y dash and z dash, okay. And next x y dash, x y dash, and x z dash is included here and here, okay. No need to represent one time once again. I can reuse that, okay. I can reuse that, okay. And next if you see, this is y, y what is it, y z dash, think y yz, so sorry, yz, this is yz, okay. So what is my a equal to what? Xy xz dash, okay. And x y dash, xz dash, xy dash, yz, yz, it is connected to b, okay. Like this we can implement PLDs. PLDs are nothing but programmable logic devices. In this, you will get three types. One is programmable read-only memory, programmable array logic, programmable logic array. Programmable read-only memory is nothing but what? So you have a fixed AND array and programmable OR array. They will implement with decoder. PAL is nothing but programmable AND array and fixed OR array. Okay, so this I implemented. PLA is nothing but programmable. Both are programmable. Programmable AND array and programmable OR array. Okay, this is about PLA. And next we'll see the RTL design. RTL is nothing but register transfer level. So how the data is transmitting in the register is nothing but RTL. Okay, basically by using Verilog we are using. Okay, so this is the basic design flow. Suppose you'll come with specification. Okay, like if it is any IC is there, for which purpose that IC is operating. Either it may be communication, or it may be networking, or it may be computers. That is nothing but they come with specification. How much power it will take, how much area it will take. Okay, and like that. Okay, so that means here most experienced people, 25 years above, architecture engineers are there. That is, those will do the specification. Okay, RTL design means RTL designers will design this RTL design. And next, GDS2 means what? GDS2 means graphical uh, data graphical display system. Like GDS2, it will be generated, and next it is given to the IC. This is fabrication. Okay, so basically, front end and back end will be in between. Front end and back end it is there. This is ASIC flow. Okay. So coming to the HDL. HDL is nothing but basically like you have high level languages. What are high level languages? C, C++, Java, okay, Python. Okay. So what is the difference between high level language and HDL means? These people can develop the application only. They can develop the application. Suppose banking system is there. They can write the program and they can develop the application for banking system. Suppose ATM machine is there. ATM programming is there. Okay, they will develop the application only. Railway ticketing is there. So they will develop the application only. Okay, like that. But HDL we can generate the hardware. Generate the hardware. HDL is nothing but you already studied in the digital combinational and sequential. How you are describing the circuit in terms of textual form is nothing but HDL, hardware descriptive language. Okay. So there are some properties are there, like it can be executed parallelly in the hardware. Okay, it will support some syntax and semantics. Okay, and so what is the difference? So these are two HDLs are there. One is Verilog, another one is VHDL. So what is the difference between Verilog and VHDL means? Verilog is a high level design and easy syntax, easy to learn, and multi-level abstraction. So if you are comfortable with C, mostly it will follow C syntax only. Okay. Suppose example, AND gate is there. AND gate, I wrote this AND gate. So what is this A, B? What is my output? Y equal to AB, no? So with Verilog, so it will start with module, and this is nothing but we can call as a module name or identifier. Okay, so and underscore get identifier. I need to initialize input A comma B, output Y. Okay, assign Y equal to what A and B, and end module. So this is nothing but bitwise and operator. Okay, by using bitwise and operator, I am using continuous assignment statement assign Y equal to A and B. So within how many lines my code is completed? 3 lines. Okay, if you consider VHDL, this is having hard syntax, controlled language, hard to learn, and multi-level abstraction in there. Okay, suppose see here, first you need to initialize the header file library IEEE. Use IEEE. Uh, one second. Yeah. So this is IEEE. So this is header file, and this is entity. You need to write the entity. Entity. You need to declare the input and output. A is in std underscore logic. B is in std underscore logic. Y is out std underscore logic. This is in entity. You need to declare the input and output. And in the architecture, you need to write the logic. Architecture arc of and underscore gate. This is identifier is a begin y equal to A and B. Okay. So for simple AND gate, how many lines of code are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11. Mostly 10 lines of code. So which one is simple? Verilog is simple, no? Verilog is simple. Okay. So that is the difference between Verilog and VHDL. And as I told you, HDL is hardware descriptive language. Okay, to describe the digital circuits, we are using HDL. Okay, hardware digital system in textual form. HDL is nothing but hardware of the digital in textual format. Okay, there are different types of level of abstractions are there. Okay, and one second. Hello, I'm in meeting, ma'am. Just can you call
Hello.
after 15 minutes? Hello,
For 2 minutes is our students.
I'm in meeting, ma'am. Actually, I'm in meeting. Yeah, so job of VLSI engineer is to design the IC which meets required functionality with best quality of results. Okay, so for low area, high performance, and low power and consumption, low power consumption. Okay, so if you see, so basically, like you have different levels of abstraction, like switch level abstraction, transistor level abstraction, gate level abstraction, RTL. RTL means you will get two types: data flow and behavioral modeling. Okay. Switch level means in terms of this normal you will represent in terms of transistor. That is switch level. You represent in gate level. Okay. You represent this in terms of gates and flip flop. RTL means so data flow means you are representing in terms of what in terms of what we call expressions. Suppose half adder if you take sum equal to what AX or B, no? Carry equal to what AB. Okay, and behavioral modeling means you will use some procedural statements like procedural blocks. Those are nothing but initial block and always block. Initial block is not synthesizable. Always block is synthesizable. Synthesizable means what? We can convert into hardware. We can convert into hardware. So we can use data flow modeling, behavioral modeling, or hybrid modeling in RTL. Okay, RTL description, we can use data flow or behavioral modeling. So we'll use some procedural statements. Those are nothing but if, case, for, while. These are there in the C language, no? And we'll use blocking assignments for combinational circuits, non-blocking assignments for sequential circuits. Okay. So blocking is nothing but that is sequential in nature. One instruction is executed, next instruction will be in blocked state. So non-blocking means what? All the instructions will be executed at a time. That is non-blocking operators. Program structure will be like this. Module. So it will start with module name, port list, okay, and end module. Okay. Port list are nothing but input, output, in out. Sometimes they will use as in out also. Okay. And declares the specify the object of registers, module items. Okay, so here you will write this module items, whatever the logic is there. This is circuit level modeling. So like we'll write in terms of transistor. Okay, so how you write this is CMOS transistor. So module, and this is basic inverter, V in and V out. Input V in and input V out. There are like supply 1 and supply 0 are there. This is supply 1 is VDD and supply 0 is ground. Okay. So this is PMOS, V out, VDD, V in. NMOS, V out, ground, V in. Okay. So mostly will not prefer this. Why? Because if you go for high level modules, by using transistor, it is very complex. Okay. Very complex. So will not prefer the circuit level modeling. Gate level modeling means we'll represent some gate level primitives like AND or NOT, NAND, NOR, buffer, buff1, buff0. Suppose example, if you take the half adder, so how you will write this is XOR gate, no? This is XOR gate and this is AND gate. Okay, so module half underscore gate output is sum comma carry and input A comma B. I'll use gate level primitive, that is XOR. It will be like this: gate level primitive, gate level primitive, and instance name. Okay, instance name, output, input like this. It will be there. Okay, so what is the output? Sum is the output, and what are the inputs? AB. Carry is the output, and AB is the input, and is the gate level primitive. End module. Okay, so like this also you can write XOR. This is nothing but gate instance of gate 1 and instance of gate 2, like this I can indicate. Okay, this is gate level modeling. So this is also we will not use RTL means we can use data flow modeling and behavioral modeling. So simple half adder you see, so input A comma B, output sum comma carry. So I'll use container assignment statement, sum equal to what? A XOR B. Sum equal to A XOR B, we know the expressions, carry equal to AB. Okay, assign, I need to use assign. By default here you are not declaring this variables, means this is a wide data type. Okay, basically you have wide data type and reg data type. Wide data type will not store any value, but reg data type will store one value. Default value for wide data type is z, and this is x. Okay, assign, continuous assignment statement, carry equal to A and B. Okay, behavioral modeling means what? So module half and half underscore behavior, input A comma B, output you need to use reg. There are some port rule connections are there. Output you need to initialize as reg. Okay, always at the rate A comma B. This is nothing but sensitivity list. This is nothing but what? Sensitivity list. Okay, begin. I'm using case statement. I told you, know, in behavioral modeling what we'll use, we can use the procedural statement. What are those? That controls execute flow within a procedural blocks. We can use if statement, case statement, for, while, repeat, forever. Okay, all this we can use. Okay, so here also I'm using case statement. So this is nothing but switch. I'm using concatenation operator. Two tick binary 0 0 begin. So you know the truth table, no? So that means what is the truth table? A B, and what is this sum comma carry. Okay, so 0 0 sum 0 carry 0 0 1 sum 1 carry 0 1 0 sum 1 carry 0 1 1 sum 0 carry 1. So based on that only I am writing. If input is 0 0 sum 0 carry 0, input is 0 1 sum 1 carry 0, input is 1 0 sum 1 carry 0, input is 1 1 sum 0 carry 1. Okay, end case, end module. Okay, like this. Okay, so this is about RTL, register transfer level. And I want to show you one program related to this ALU, 4-bit ALU. Just I will explain this 4-bit ALU. Yeah, 4-bit ALU. So this is Xilinx Vivado. So Xilinx Vivado, we can write the Verilog code and we can simulate and we can elaborate the waveform like that. Okay, so just I'm expanding. One second, see here. So this is my 4-bit ALU. First I need to initialize what? Module, my module name, ALU underscore 4-bit, input clock, input reset underscore n, input. So 3 down to 0 is nothing but this is a vector. How many bits? 4 bits. Input 3 down to 0 B. Okay, I'm using one more control also. But depending on the control only, it will do some operation. Input 2 down to 0 control, Output I need to give as reg. Why? Because I'm using behavioral modeling now. So output reg 3 down to 0 result always at the rate passage of clock or negate of reset. That means what? You have two types of resets are there: synchronous reset and asynchronous reset. Synchronous reset is nothing but synchronous reset removal and reset applied, both are synchronous with the clock. Okay, so that we are not using in the industry. Asynchronous reset also you have like active low reset and active high reset. Okay, so active high reset also we are not using. So active low reset we are using. So active low reset, reset applied. So when it is going from reset mode to functional mode, reset applied is not reset. Sorry, reset removal is what synchronous. Whereas reset applied is asynchronous with the clock. Okay, so that too active low I'm using. Why? Because active low means you are using your design when the power is off. When the power is off, we are using that design. Okay. Suppose if you use active high, so you are giving some power to make that reset to high. Okay. So that's why I'm giving this asynchronous active low reset. So sometimes one my clock will not work. Okay, so sometimes my clock will not work, so I need to reset my design. So I can't reset now. So that's why even though clock is not there, I need to reset that circuit. That's why I am using this is nothing but asynchronous active low reset. So in the sensitivity list, I give passage of clock or negate of reset begin if not of reset. Okay, if not of reset, if reset equal to 0, so I need to reset results. I need to reset the result to 0. Okay, end. Else begin control. Control I have given how many bit? 3 bit, no? So 3 bit means what? 0 0 0 it will do like bitwise AND operation. 0 0 1 it will do bitwise OR operation. 0 1 0 it will do addition, and remaining bits I am not using. And if it is 6 1 1 0 I am using subtraction, and 1 1 1 I'm using equality check. Okay, this is default. This is nothing but default. Okay, so this is my like Verilog code, and this is my test bench. Test bench, how you should write a module TB ALU 4 bit. Whatever the input variables are there, that I need to consider as what we call reg, and output variables I need to consider as y. I need to instantiate that design. How I am instantiating? That is nothing but my design name. My design name is ALU underscore 4 bit unit under test, and whatever the output variables outside the bracket are nothing but design input and output, and whatever the variables inside the bracket are nothing but test bench input and output. Okay, by test bench you are giving the stimulus to the design, so that design is the design is calculating the processing the input and output, and it is giving the output to the test bench like this. Okay, just you are verifying whether your design is correct or not. Okay, so clock generation, you need to generate the clock. How you generate the clock? Initial clock equal to 0. Always hash 5 clock equal to not of clock. Okay. And next I'm initializing test A, test B, test control. This is how many bit means this is 4 bit only. Okay. This is 4 bit only. And test control 3 bit I'm using. Okay. And initializing the text vectors. Okay, test A I'm giving this value, test B I'm giving this test control. It should do AND operation. Okay, normally this is 1010. Yeah, okay. Mm, just to mute, sir. Yeah. So these are the test vectors I need to give for OR operation, AND operation, subtraction, equality. I need to give. And now applying the reset. Reset equal to 0. That means it will make the reset to 0. 12 5 minutes I'm checking, and making reset equal to 1. By using for loop, I'm giving the text vectors. Okay, text vectors, text cases I'm giving. Okay, text cases. Okay, and after that applying again synchronous reset, again reset equal to 1, and stopping the simulation. Okay, this I want to like simulate. First I want to see the how the design will look like. So that means I wrote the program. Whatever the tool is there, tool will make the hardware only. Okay, So I wrote a RTL design. I want to elaborate the design. Okay. See here, when I am elaborating the design, here creating the netlist. Just we'll see how the design will look like. Okay. Yeah, tell me, sir. Yeah, yeah. Okay, okay, sure. Okay, sure, sir, sure. Yeah. So this is my design. See here, this is my design. So this is four inputs are there, and it is set underscore n clock and control. Okay. So when it is 0 0 0, it is selecting AND gate, 0 0 1 OR gate, and 1 1 0 it is selecting. So I think it's visible. So 1 1 0 it is acting as the adder, and like that. Okay, depending on the selection line, it is acting as a different equality operator, and it is given to 8 cross 1 mux. And here you are using D flip flop. You are using D flip flop. Okay, so this is my elaborate design, and I want to simulate this. Just run behavioral simulation. Run the behavioral simulation. Yeah, you can see in the TCL console also. Here output, you can see the TCL console. See here, I think I didn't given the display statement. That's why I'm not getting TCL console. You can see in this simulation part. Okay, see here for different values depending on the control. See here. So so initially, see here, here based on the reset, I will explain. When reset equal to 0, the output will be like unknown only or 0 only. Okay, so this is nothing but what reset mode. When it is going from reset mode to functional mode, so when you are getting the output means during the passage of clock. During the passage of clock only. See here. Result when you are getting during the passage of clock only you are getting. So that means, as I told you, like reset removal is synchronous. Reset removal is synchronous. Depending on the control, okay, control equal to 0 means it will do AND operation. Control equal to 1 means it will do OR operation. Like that, it will do this different types of operation. And till here, this is functional mode only. Okay. After that, what happens? Here you see, it is again going from where to where. It is going from functional mode to reset mode. Okay, as I told you, like as it going from reset mode to functional mode, this is synchronous with the clock. When it is going from functional mode to reset mode, this is asynchronous with the clock. Irrespective of clock, okay, irrespective of clock, directly it is making the output to 0. Directly it is making the output to 0. Okay, so like this you can analyze the simulation part. Okay, this is about the simulation and elaborate design and all those things. Okay, so hope you understood this today's session. Today we covered this first we covered the MOSFET as switch, and next we covered the how the MOSFET is acting as a switch, and next we covered the MOSFET as a amplifier. Okay, how it is acting as an amplifier, and we discussed about the common source amplifier, and next we discussed about the BiCMOS inverter. So how the BiCMOS inverter is there, how the operation, why we are going into the BiCMOS by adding the advantages of both bipolar and CMOS. We are designing the BiCMOS technology, and we discussed about the inverter. And next, we discussed about the implementation of inverter and NAND gate and NOR gate by using this NMOS technology, CMOS technology, and BiCMOS technology. And next, we seen about RTL design. What is the purpose of this RTL design, and how many, like what is HDL? Okay, what is HDL? What is the difference between high level language and this HDL? And and next, we've seen about the difference between VHDL and Verilog. Okay, with Verilog we are seeing, and different levels of abstractions we've seen: switch level, gate level, data flow level, and behavioral level. And next, we seen the examples with respect to each and every styles. Okay, and next we see in the program related to Verilog program related to ALU 4-bit and test bench. We elaborated the design and we see in the simulation part. Okay, so this is about my session. Any doubts or any queries you can ask me.